Hello guys. So today in this video, we are going to talk about the last two ways to calculate enthalpy, which is using basically the energy of bonds and then also just the energy that it takes to create the standard enthalpy of formation, I guess. So yes, that's what we will be doing. You're probably going to want a calculator for this video and of course your notes. So let's get started. So the first thing I want to point out is that these two methods are very similar. So it's really important that you pay attention to what kind of data you're given. Are we given the energy of bonds or are we given the enthalpy of formation? So it's really important that you pay attention to that because that's going to be really crucial in determining your formula. If you do it opposite, because they're very similar, you're going to end up with the wrong answer. All right, so let's start, and we're going to start by talking about heat of formation and the standard enthalpy of formation. So standard enthalpy of formation is basically how much energy does it take to make a compound from its elements, from what it's made up of. It always happens in the standard state at 25 degrees Celsius. So standard state would just be like state at 25 degrees Celsius. Yeah, and so we can actually use how much energy it takes to make our products or reactants to figure out our overall energy change of our equation. So that's kind of what we're going to be talking about today. So sometimes you may be comparing bond strengths. Who's got a stronger bond of our reactants to products. So our products of endothermic reactions are going to have weaker bonds than the reactants. And products of an exothermic reaction are going to have stronger bonds than the reactants. Okay, so we're going to jump in. This problem is kind of more a stoichiometry problem than it is going to be what we're doing today, but it does go along with what we just talked about the bonds. So let's hop in. So it says the enthalpy change for the reaction represented by the chemical equation shown above is that our delta H is 2,357 kilojoules per mole of reaction. When 3 moles of NH3 reacts completely with an excess of oxygen, what is the change in enthalpy? Would the bonds in the products be stronger or weaker than the reactants? All right, so we are going to basically use a mole-to-mole ratio here to help us figure this problem out. So we're going to start with ammonia. So I have 3 moles of ammonia. And from my chemical reaction, I know that for every 4 moles of ammonia that react, it's going to require 2,357 kilojoules of energy. And we'll just solve that. So since that's what we want, so energy. So let's go ahead and plug it into your calculator. So 3 times 2,357 divided by 4. Should have 3 sig figs, so you should get 1,770 kilojoules. This is an endothermic reaction, so it does ask, would the bonds of the products be stronger or weaker than the reactants? It is an endothermic reaction because our delta H is positive, so it tells us that it's endothermic, so that means that our products would be weaker. All right. So that's just a little kind of aside almost. So let's go back to talking about enthalpy of formation. So we talked about how whenever we're getting the enthalpy of formation, that it's in its standard state. So that kind of has some factors that go with it. So like for gases, if it's a standard state, it's 1 atmosphere. For substance in solution, that means our concentration is 1 molar. Pure substance in a condensed state, so liquid or solid, our standard state is going to be all liquid or all solid, like pure liquid or pure solid. Yeah. And then for an element, the standard state is the form in which the element can exist under conditions of 1 atmosphere and 25 degrees Celsius. It's kind of like saying like room temperature and pressure. Here in Texas, our pressure is typically around 1 atmosphere. Sometimes it's a little more, sometimes it's a little less, but it's pretty much around that for us. All right, one thing to note, a lot of times you will be given these heat of formations or given enough information to solve for what you need. But one thing to note is that if it's just a pure element, its heat of formation is going to be 0. It doesn't take any energy to form pure elements. And you can find these delta HF values in your textbook if they're not given to you in the problem. All right, so our reaction is going to be that our change in enthalpy is equal to the sum of our change in enthalpy of our products minus the sum of the enthalpy of formation of our reactants. All right, so let's work this first problem. So it says consider the reaction 2ClF3 plus 2NH3 yields N2 plus 6HF plus Cl2. And it does actually give us our delta H, which is 1,196 kilojoules. Using the information in the table below, calculate the delta HF for ClF3. All right, so let's kind of plug in our data values. So we know that our delta H of our reaction is going to be equal to the sum of the heat of formations of our products. So the sum of our products would be N2, heat of formation of that, plus 6 times the heat of formation of HF, plus 1 times the heat of formation of chlorine, minus the sum of our heats of formations of our reactants. So 2 times the heat of formation of chlorine trifluoride plus 2 times the heat of formation of NH3. Okay, let's plug in the values we have. So we know that our delta H is 1,196 kilojoules. Our heat of formation of nitrogen is going to be 0 because it's an element. Even though it is N2, it's still an element, so it's going to be 0. Plus 6 times the enthalpy of formation of HF, so negative 271, plus the heat of formation for chlorine, also going to be 0 because once again we've got an element, minus, again, we don't have our heat of formation of chlorine trifluoride because that's what we're looking for. So minus that plus 2 times the heat of formation of NH3, which is going to be negative 46. All right, guys. And then, from there, we're just going to kind of start simplifying. So I'm going to add up all together, kind of start simplifying over here. So I would get 1,196 kilojoules is equal to, when I add all of the first part up together, I get negative 1,626 plus, or I guess minus, but plus over here, negative 2 times my chlorines plus negative 92. All right. Keep going, keep moving, keep shaking. And, oh, I'm sorry, this should be positive 92 because it was negative. So then keep moving, shaking, keep simplifying this reaction here. And if I do that, I get 2,000, kind of combine my like terms, move things all over to one side. I get 2,730 is equal to negative 2 times the heat of formation of chlorine trifluoride. So when I solve for the heat of formation of my chlorine trifluoride, I would get negative 65, not 56 kilojoules. All right, let's do the next problem. So it says, using the information in the table below, calculate the enthalpy for the reaction below. And then we are given our reaction. We have heats of formation here, so that's what we're going to use to solve for our delta H here. So once again, it is our, if we go back up, it is our heat of our reaction, our enthalpy, is equal to the sum of the heat of formations of our products minus the sum of the heat of formations of our reactants. All right, so let me get this situated and let's write out our equation. So delta H will be equal to the sum of our heat of formation of 1 carbon dioxide plus 1 water plus 1 nitrogen minus the sum of the heat of formation of CH2 N2 plus oxygen. All right, let's start plugging in our values. So delta H is equal to negative 110 kilojoules plus negative 285.9. It's nitrogen. It's a pure element, so that's going to be 0 minus the heat of formation of CH2N2, which is going to be 62.4, plus oxygen, which again is an element, so it's going to be 0. Okay, so then we'll just plug that on into our calculator. So go ahead and take a minute and plug it in. And whenever I plugged it in, I got that our heat of reaction should be negative 458.3 kilojoules. All right. Why don't you guys go ahead, pause this video, and work this next problem. You're just finding the delta H, the heat of the reaction. So you guys just go ahead and pause this video, work out the problem, and then check back to see if you got the right answer. Okay, guys, so you solve that whole problem. You do all of the heat of formation of your reactants, of your products minus all of your reactants, and plug it all in. There's quite a few there, but when I plugged it all in and plugged it into my calculator, I got negative 2,677 kilojoules as my heat of reaction for that one. Okay, so that's our first reaction, and it's, delta H is equal to our reactants minus our products. I always remember that equation as it is hot in Puerto Rico. So our delta H is equal to our products minus our reactants. So so that's our first reaction. Now, you guys, you know to use that one because it gives you the heat of your formations. And that's when we're going to use products minus reactants anytime we're given that heat of formation. Now, our next equation is bond enthalpy, and it's very, very similar, but it gives us the energy of bonds in a reaction. And so it's going to end up being slightly different than this one that we're talking about. So breaking bonds requires energy, takes energy to break a bond, and making bonds releases energy. So the energy required to break bonds and the energy released when making bonds can be used to determine the enthalpy of a reaction. And here, our equation is that our delta H of our reaction is equal to the sum of the energy of our bonds broken minus the sum of the energy of our bonds formed. Now, where are bonds broken? On what side of our reaction do our bonds break? Well, our bonds break on our reactants. And then where are bonds formed? Our bonds formed happens on our product side. So this reaction is going to end up being opposite because it's going to be the energy that it takes to break our bonds minus the energy that is released when we formed. So it's going to be reactants minus products. So you guys see how they're very similar, but just have slight differences to them. So So let's jump in on this one and work our first problem. So this one says the reaction of N2 plus H2 yields 2NH3 proceeds accordingly. The table above provides the average bond enthalpy for selected bonds. Calculate the calculate enthalpy change for the reaction is 93.82 kilojoules per mole. What is the mathematical procedure to estimate the bond enthalpy per mole of NH3? You know what, guys? We are not going to, we're not just going to estimate. We're going to go ahead and solve this one. So we're going to cross out this what is the mathematical procedure, and we're just going to say estimate the bond enthalpy per mole of NH3. And basically, what we want to do is we want to figure out what is the energy between an NH bond, and we're going to compare it to the table above. All right? So let's figure that one out. So the first step in these problems is going to be have to figure out what's actually going on in my reaction and how many bonds are broken and how many bonds are formed. So like right here, I have N2. So I need to draw out N2. So it means it looks like that. It's two nitrogens bonded together with a triple bond. H2 would look like that. A hydrogen single bonded together. Then NH3 looks like this with a lone pair up top. So guys, if we're doing bonds broken versus bonds formed, we need to figure out how many bonds are broken, how many bonds are formed. To do that, we need to balance our equation. So two nitrogens, two hydrogens, 6 hydrogens. That means I need a 3 there. So I have 1 nitrogen, 3 hydrogens, and then 2 NH3s. So let's look at our bonds that are going to be broken and formed here. So my nitrogen to nitrogen bond, I have 1. My hydrogen to hydrogen, there are 3. And my nitrogen to hydrogen, there are 6 bonds there. Okay, so if I want to find out the bond enthalpy of NH, all right, based on my problem, I want to find the bond enthalpy of NH, all right, and then I'm going to compare it to the table, see how close it is. I'm going to go ahead and plug in my reaction this way. So delta H of our reaction is going to be equal to the sum of our bonds broken. So bonds broken is going to be our reactants. So I'm going to have 1 nitrogen to nitrogen bond broken, plus I'm going to have 3 hydrogen to hydrogen bonds. All right, minus those of our bonds formed. So we are going to form 6 nitrogen to hydrogen bonds. All right, that doesn't really need to be in parentheses there. So 6 nitrogen to hydrogen bonds. All right, so now we can go ahead and plug in our data values. So our delta H of our reaction is from our problem 93.82 kilojoules per mole. It's equal to, and our energy of our nitrogen triple bond is 941 plus, and we only broke 1 bond there, 3 times our hydrogen bond, which is going to be 432, minus, and it wants us to, like I said, we're going to find our NH bond there, so times 6 times our NH bond enthalpy. 6 times that. And I'm actually, instead of using NH, I'm going to use X since it's a little easier to write. So minus 6X. All right, go ahead and simplify down what we can. So I got 93.82 equals 2,237 minus 6X. So then negative 2,143.18 is equal to negative 6x. So then x would be equal to 357 kilojoules. So right there, we were finding the bond enthalpy of NH3. So the NH bond right there. So each NH bond would have 357 kilojoules. According to our chart, it has 386. So that's pretty stinking close. Those are average bond enthalpies. Each compound may have a slightly different energy of the bond there. So that's pretty stinking close for that one. All right. Cool. Sometimes you may not get a close answer. That's okay. All right, so why don't you guys go ahead and try to do this one, and then we'll go over it. All right, so pause your video, try to do the last one, and then we'll go over it. All right, guys, so I have solved it. So the first thing I did is I figured out all my bonds. So I have 2 hydrogen to hydrogen bonds being broken here. I have 1 carbon to carbon double bond, and I have 4 carbon to hydrogen bonds. All right, and then I just plugged it on into my equation. Obviously, carbon is a single element, so it doesn't have a bond there. So delta H is equal to bonds broken minus bonds formed. So my bonds broken are my hydrogen bonds, minus my bonds formed is going to be my double bond in my ethene between my carbons, and then my carbon and hydrogen bonds. So I plugged in my values. We're looking for the double bond in the carbon here. And when I solved it, I got negative 840 kilojoules per mole. Now, it says it's normally 614 kilojoules per mole, so I'm thinking there must be something a little off about this problem for us to have gotten negative 840. All right, guys, so that is the last little bit of how to solve for enthalpy. Yeah, all right.